Okay, so on page 2, we're just making some abstract art similar to what we saw on the cover. Abstract art is a non lifelike representation of real world objects, people, and scenes that are usually difficult for other people to recognize. Abstract art shows what an artist feels and thinks more than what he or she sees. An abstract artist uses color and shape to express his or her emotions and ideas. Just as we do not know other people's thoughts, we do not always know what abstract art portrays. But if you ask the artist, he or she can explain the painting to you. Try to create a work of abstract art. Begin your drawing by placing 11 small dots at random in each of the boxes below. Within each box, start connecting those 11 dots with lines. Think of the dots as places for the lines to connect to different ways. The 4 different boxes let you explore variations that come with the placement of the dots on the page, their proximity to one another, and how your image develops using different techniques and colors. Remember, the only rule is to simply connect 11 dots with lines. Creating abstract art works best when you approach the challenge spontaneously. Don't overthink it. Yeah, you do 11 different ones. Well, excuse me, 11 dots, 4 different times. All right, I think let's stop for now and you can go back to that later. And let's move forward with the lab. So I don't know if you guys have used the feature that allows you to jump from the top of one page to another, but I like using that. It's up here at the top. It's these up and down arrows. Let's go to the top of page 3. And notice every page has this little preview at the top of it, right? So here's a new equation for us. In physics, we often are able to convert our measurements into equations, right? So this one, wave velocity, in other words, how fast a wave is moving, like the speed of sound is something like 750 miles an hour. That's the velocity of a sound wave. And that sounds like a lot, but it's nothing compared to the speed of light. Which reminds me, on page 11, I asked you guys to do 9, 10, and 11 on your own, right? The first question on page 11 was a math problem that might have been challenging. And I created a document and posted it on Teams as an assignment to help you solve that problem. It's not really an assignment by itself, so you don't have to worry about completing it. If you want to check it off that you turned it in, you can do that just to get it off your to-do list, right? But the only thing it is how to solve the problem. So if you're stuck on page 11 on the math, look at that document. If that doesn't help, then talk to me about it. At any rate, wave velocity is how fast the wave is moving. And if we take the frequency, in other words, the number of waves per second, which we, at least with sound, we measure in hertz, named after that's, I think, a German scientist. We take the frequency and we multiply that by the wavelength. That's literally how long the wave is. Okay? Some waves are incredibly tiny, especially with light, microscopic from one wave to another. And others are huge with light also. It might be even a kilometer from one wave crest to the next, a huge wavelength. If we multiply the frequency times the wavelength, we get the speed of the wave, the velocity of the wave. Okay? And then one of our driving questions for this whole unit, what are the properties of a wave? Well, frequency and wavelength are some of them, huh? We also have amplitude. How tall is that wave? How are those properties mathematically related? Well, right here, it tells you what the answer to part of it, huh? Frequency times wavelength gives velocity. But what we're going to do now is we're going to look at a YouTube video. You guys don't need to look at it on your computer because I'm going to play it through the screen up here. And basically, this is a video of me doing a lab with a Slinky. I set up a camera in my garage looking down on the ground. And then I took the Slinky and I made waves on the Slinky, just like we did in class the other day, right? Yeah? So we could see the wave going through there. But I did it on the ground, and I did it on top of a long sheet of paper that had measurements marked on it, so that we can measure the wavelength, so we can measure the amplitude of this wave. Okay? So I think you guys that are at home should open this link because I don't think the sound is going to come through the computer very well to you. I'm going to be starting and stopping the video as we go to help you answer the questions along the way. And you guys at home should be starting and stopping it with me. And this same thing is going to happen when we switch roles, right? When do you guys have this class again? Thursday, but you're at home? Is that right? Yeah. So Thursday, when you're on the computer screen, you're going to watch the video for yourself. And again, I recommend you have the meeting on your phone and the document and the YouTube video on your computer, right? And that way you'll know when I say, okay, stop the video, right? Or you'll see me stop it by looking at the screen, okay? So you're gonna kind of go back and forth. We're doing 3 things at once. We've got a meeting going, You've got the project going, and we've got the video going, huh? It's a literal three-ring circus. So hopefully it's going to work out okay. At any rate, we're going to start the video now. Just just for a minute to look for the answer to question 1. So before I started, everybody read question 1 so you know what you're listening for. Okay, here we go. Hey guys, welcome to my garage where we're going to do some experiments to demonstrate different aspects of waves. So what we're going to do is we're going to use a Slinky to demonstrate different components of a wave as it's moving down the length of the Slinky. Just like the air can transmit sound waves, light waves can move through space, waves can move across the surface of the lake, just like those things are transferring energy down them, so a Slinky can transfer energy from one end of the Slinky to the other in a wave. Okay, I think that actually should give you something to talk about on question 1. How does the wave transfer energy? Well, I think maybe if I give you a couple more ideas to think about, it would make sense. So here's the Slinky, right? And it passes a wave down the length of it. There's different ways it can do that. You could bounce it back and forth. Isn't that a wave action? And then there's waving it back and forth like this, right? Both of those are waves. But what would happen if the Slinky was broken right here? Would that wave transfer all the way from one hand to the other if it wasn't connected? Right? There has to be a way to transmit the energy of the motion in one hand to the other hand, huh? Right? Let's see if I can. I can't figure out how to do this while holding it, but there has to be a way for the energy to go from this hand to this hand, huh? Now with the Slinky, it's because it's this one piece of metal, huh? And when the energy is given to this coil right here, what does that do to the next coil? It transmits the energy to that coil, which then is going to give the energy to the next one, which gives the energy, right? So the energy is passed in the Slinky from one coil to another, isn't it? What about a wave on the water? Is that from a disturbance of the water surface? There's some form of energy that created the wave, right? Maybe it was wind. Maybe it was a boat. Maybe it was a rock that got thrown in the water. But somehow that creates this disturbance of a wave, doesn't it? Now think about that. You can watch the wave come into shore, can't you? Like sometimes when there's a big windstorm, it's fun to go down to the lake and watch the waves come in and crash against the shore, right? And you see, oh, there's a big one coming, right? And here it's coming, and then the energy of that wave is moving across the surface of the water, huh? The crazy thing, though, is that the water molecules themselves that were way out there are not the ones that are hitting the shore. Just like when I make a wave with the Slinky, is this first coil? Uh-oh. Is this first coil that moves? Is this coil actually moving to my other hand? Or does it just transmit the energy from one coil to another? The same is actually true of waves in the water. They lift the molecules up and then drop them back down again. And they might push them a little bit along the way. So actually the water molecules that they've analyzed make a circle with every wave. They rise up, but then they fall down again. The next one picks them up again. Have you ever tried to Let's say you had a stick or something out in the water and you're throwing rocks at it to try to get the waves to push it back to shore. It doesn't work very well, does it? Because mostly those waves just lift it up and down. Okay, so the energy is being transmitted along what we call the medium. So the material that's transmitting the energy, in this case, the coils of the Slinky, that would be the medium. For sound, the medium would be the air molecules that are vibrating back and forth. So say something about how energy is transmitted by the disturbance that created the wave. So a wave is really a disturbance of energy that is transmitted from one place to another. Okay, we're going to go back to the video and we're going to do a diagram of these waves moving down the length of the Slinky. So what you're going to see and what we're going to do is make some measurements using these marks on this paper. So every one of these marks is 10 centimeters apart. Every fifth mark is bigger. Every 50 centimeters is bigger, just to make it a little easier for you to measure. So you're going to be measuring like the peak of the wave and the length it takes to reach the next peak. That will be the wavelength, for example. We'll also count how many waves go by in a given time. So we're going to make a bunch of measurements in this lab using the Slinky as our demonstration. So if I stretch this out, and I send just a single wave down the length of the Slinky, you can see it bounces off of the wood at the end. It gets reflected back. Now there's a couple things to notice. One, how tall is that wave? And the way we can measure that is with the tops of these marks. This is 10 centimeters right here, and this would be 20 centimeters from the center line. So we can actually measure if it's a smaller amplitude or a taller amplitude wave. Now what's particularly interesting about this single wave, watch what happens and specifically watch which side of the center line the wave moves down and which side it comes back on. Did you see that? So when I move the wave to the top of the page, the wave stays on that side, but when it bounced back, it came on the bottom of the page. So the reflection, in a way, was the reverse of the original. See it? So a lot of times, people would think that the wave, if here I go again, juggling this Slinky here. And then it gets tangled and I have to spend time untangling it. At any rate, if this is the center line, a lot of people think the wave is going to go up over it and then back down it, huh? Crossing the center line every time. Is that what happened? Did the wave go up above it and then down below it? Let's watch again. Look for that. Did it cross the center line or not? A taller amplitude wave. Now what's particularly interesting about this single wave, watch what happens and specifically watch which side of the center line the wave moves down. You see that? And which side it comes back on. You see that? A taller amplitude wave. Oops, sorry. Now what's particularly interesting about it comes back, it came on the bottom of the page. So the wave, watch what happens and specifically watch which side of the center line the wave moves down. And which side it comes back on. Did you see that? So it doesn't cross the center line until it reflects back, huh? It's not like it's going above it and then below it and above it and below it and then bounces back. Instead, it stays above it the whole time, moves down the length of it, and then comes back on the other side, huh? Right? So you're supposed to draw that using labels and different colors on that diagram. Show the wave going one direction and then coming back the other direction. So when I move the wave to the top of the page, the wave stays on that side, but when it bounced back, it came on the bottom of the page. So the reflection, in a way, was the reverse of the original. See that? Kind of like in a mirror. Came out backwards, huh? Here it is in slow motion. So it's all on the top, isn't it? Then when it reflects back, it's all on the bottom. So how's it going out there in TV land? Give me a thumbs up if you're staying with me, if you got the video going and so forth. Thanks, Ozzy. All right, Rochelle and Hans, good job. Are you guys able to hear the video out there okay when I play it? Is it working better to just watch it on yours with me showing it, or is it better to have it on your own screen?
I can hear the video when you play it.
Okay, that's good to know. I guess that's because I have it coming through some speakers pretty loud, so that should work well. Also, I'm doing it through a different computer than this one, so I think that allows it to pick up the sound. Good to know. Oh, and then it says you don't need to draw the coils. And what I mean by that is you don't have to draw the thing shaped like this, right? Just like a line going up with a wave in it and then coming back. Okay. We're in the middle of a lab. I just give him a note to go see you. Okay, thanks. So I'm hoping that when you drew this, you did something like, I don't know, you showed the Slinky with a wave in it. It's not easy, is it, to draw with this thing? And then it hit the other side, right? And I'm going to change color here. You don't have to, I suppose. But then when it came back, oh, it changed both of them. Darn it, I didn't want that to happen. Let's see if I do this. Yeah, I found that if, like right then, it tried to um, change the color of both my lines. But if I tell it that I'm going to type, if I switch commands to typing, and it don't even type anything, then I can go back. Then I can go back and it will keep the two different colors. Now, the other thing I want you to do is make sure you included arrows showing which direction it's going. And, you know, there's a shortcut for drawing arrows in here. If you go to the shapes, you can put an arrow in, and it makes a nice arrow for you. Except I'm going to change the color of that one to match the color that I used in that direction. At least I think I'm going to. I guess not. So I'm going to delete that guy and do it again. Use the arrow command. I'm going to use blue. And it's going, still making a red arrow. I wonder why that is. And then it's coming back on the other side. Is that what we saw? Yeah. Right? Which is a little surprising to me. I would have imagined the wave would have crossed over both sides, huh? Crossed over that center line. And then it's kind of cool in the reflection that when it bounces back, it's also on the other side, huh? And then when it hit my hand, I don't know if you noticed this, but when it came back and hit my hand again, it reflected again. And did you see on that reflection, it was now on this side, right? It kind of went from like positive to negative every time. Also, the size of the wave shrunk the further it went too, didn't it? The energy was being dissipated. And then you should have some labels. Got to go fast because we're doing a lab. And you should have some labels on this too. So what are you going to label? I would label the original wave, and I would label the reflection. Original wave and reflected wave would be good things to add. And when you're done with that, go down to the next section about wave speeds. We're going to compare the speed of a high amplitude to a low amplitude wave. Remember, amplitude is how tall the wave is, how big the disturbance was. So, for example, when I'm out on my paddleboard, I don't want high amplitude waves. I want the water to be flat. I want very low amplitude waves or none at all. Sometimes a boat goes by and it knocks me down, right? Because the wave is so big. On the other hand, if you're out surfing, you want really high amplitude waves, right? You want to ride that big wave. So think of amplitude as the height of the wave, the intensity of the wave. And what I'd like you to do is start on number one by making a prediction or a hypothesis. Try to answer the question, will a large amplitude wave or a small amplitude wave move faster? What do you think? Which one will move faster? I also want to remind you that whenever you make a prediction like this, there's really three options. You could say the large amplitude wave will move faster. You could say the small one would move faster, or you could predict that there will be no difference between them, huh? any of those is a valid prediction. So what do you think? Well, that tall wave that's made by the speedboat, will it move faster, or will it move at the same speed, or will it move slower than a smaller wave made by, I don't know, a canoe? Or maybe we should be focused less on the boat and the water than we should about like a light wave. Will the high intensity light wave move faster or slower than the low intensity light wave? And then you're going to get out a stopwatch. So you want to get out your phone and set it to stopwatch mode, because we're actually going to do this part of the lab where you're going to measure these things for yourself. I'm going to do the movement of the Slinky on the video, but you're going to measure it, okay? So it's trying to get you guys involved as much as I can, but thank goodness I didn't unplug my computer. And then we're going to move on. So everybody should have a stopwatch ready to go, because it's not going to give you the times, right? You're going to measure those yourself. Okay, so now we're going to get into actually doing some experiments. And the first thing I want you to do is make a prediction about how fast the wave is traveling. I want you to make a comparison between a small wave and a large wave, a low amplitude versus a high amplitude wave. Which one do you think will move faster? So let me show you what I mean. I'm going to move my hand just a little bit for the first one, and I'm going to move it a lot for the second one. Which one will get back to my hand faster? So I'm going to have you start a timer. So you need a stopwatch. You can use your phone, would be great. I'm going to count down. I'm going to say 3, 2, 1, and then go. When I say go, I'll start the wave moving, and then you stop your timer when it hits my hand, when it bounces back to my hand. But first predict, which do you think is going to take longer? Which is going to be the faster wave? Will it be low amplitude wave or the large amplitude wave be faster? Or of course you can always predict that they might be the same. So what do you think? Which is going to be faster? Small amplitudes, which is the height of the wave, or large amplitude wave? Here we go with the small amplitude wave. Okay, so what I'm going to do on the video is I'm going to say 3, 2, 1, now. Or I think I say 3, 2, 1, go. And you start your stopwatch when I say go. 3, 2, 1, go. And then the wave is going to go down to the block of wood. It's going to come back to my hand, and I'm going to say now when it hits my hand, when I feel it. Okay? So that's when you stop your stopwatch, is when I say now. Start it when I say go, stop it when I say now. Does that make sense? Yeah. And for each of these, you can see on your project that we're going to do them 3 times each, and then we'll take the average. Okay? I'm also going to do an instant replay later in case you missed one of the timings. All right? So have your stopwatch ready. Listen for the go is when you start it, and the now is when you stop it. You ready with your stopwatch? 3, 2, 1, go. Now. When I said now is when I felt the wave hit my hand again. Let's take. Do you want to, was that a practice one, or do you want to do it again? Or keep going? That was a practice? Don't forget to reset your stopwatch, okay? Make sure you reset your stopwatch. Here we go with the small amplitude wave. Be ready. You ready with your stopwatch? 3, 2, 1, go. Now. When I said now is when I felt the wave hit my hand again. Let's take the average of 3 of those, okay? All right, so record that value in the first part of the chart. Make sure it says small amplitude, trial 1, I think is what we're looking at. Yeah, small amplitude wave, trial 1. And then we're going to work across the chart, right? Okay. Reset your stopwatch. Get ready for trial 2. Small amplitude wave number 2. Counting down. 3, 2, 1, go. Now, third one. Go ahead, record that. Trial 2, small amplitude. Reset your stopwatch. Ready? Nice. All right, here we go. Counting down. 3, 2, 1, go. Now.
No, I messed up.
I was a little late too on that one. Funny. So they are going to have an instant replay here. So if you need to redo one, great. If you are happy with all 3 of your measurements, then you could calculate the average. But actually, it might not be bad to double check, huh? So it's going to replay all 3 of them. So we could double check your measurements. Okay, so we're going to take the average of those 3 times. Take your stopwatch again, and I'm going to move the Slinky more. I'm going to put more energy into the Slinky. So before we do the averages, before we do the replay, we're going to do the large amplitude waves. All right, so have your stopwatch ready to go for the taller wave. Let's see what happens when we compare their speeds. Here we go, the large amplitude wave, 3, 2, 1, go. Now, and again, go ahead, record that. Large amplitude wave number 2. Again, 3, 2, 1, go. Now, when I say now is when it gets back to my hand. That's when you stop your stopwatch. Last one. 3. Okay. Last one. 3, 2, 1, go. Now. Oh, I stopped that one way too soon. Here we go with the small amplitude wave. Okay, here you can double check. Like I know that the last one for me, I cut it off too short. So I would want to remeasure that one. So if you feel like your numbers are all good, go ahead and calculate the averages. Remember to find an average, you add the 3 numbers together. And since there's 3 of them, you divide by 3, right? If you need to check your times, then do that here. Of course, it's not a bad idea to double check that you were in the right zone anyway. You ready with your stopwatch? 3, 2, 1, go. That was the small amplitude wave number 1. Let's take the average of 3 of those, okay? Small amplitude wave number 2, counting down. 3, 2, 1, go. Now, this one's also zoomed in. It's a little easier to see that the wave comes back. Counting down. 3, 2, 1, go. Now. Okay, so we're going to take the average of those 3 times. Take your stopwatch again, and I'm going to move the Slinky more. I'm going to put more energy into the Slinky. Let's see what happens when we compare their speeds. Here we go, the large amplitude wave, 3, 2, 1, go. Now. And again, 3, 2, 1, go. Now. When I say now is when it gets back to my hand. measurements when you stopped your stopwatch. Last one. 3, 2, 1, go. Now. Now, one thing you might know. Okay, so anybody need anything repeated, first of all? All right. So if you got 3 measurements, take their average, add them together, divide by 3. And it seems to me that our numbers are all pretty close together. Are you getting the same thing? Like I was getting about approximately 1.5 seconds every time. And then for the large waves, I was still getting about 1.5 seconds. Is that what you guys got too?
Yeah, I did.
Approximately, right? It was not the case that the large one was like twice as fast as the slow one, was it? It certainly wasn't 10 times as fast, or the other way around, huh? So this leads to this question of there probably was a little bit of a difference, right? But was that a true difference in the speed of the wave? Or was it more of a difference in how accurate your timing was, the starting and stopping of the stopwatch? Also, was me saying now at the exact moment that it hit my hand? So this gets to this idea of what we call a significant difference. Was it a true difference or not? Or was it just due to random measurement errors or something else? So overall, what do you think? What's the answer to your question? Which wave was faster? Which wave was truly faster? Can we even tell from this experiment? Was there very much difference? And if there was it a significant difference? Was it a true difference? Go ahead and answer questions 3, 4, and 5. Noticed is how much the reflection continues. How many times does it bounce when I do this small amplitude? And then once you've answered questions 3, 4, and 5, move on to the next page. And there's a couple of short paragraphs for you to read and highlight the important text as you go. Remember, I do give you a score for highlighting. And you guys at home, will you give me a thumbs up when you're ready to move on? Let me know if you have any questions. You can write in the comments section. So highlight the important text in the first couple paragraphs at the top of page 4. So when I asked you guys, I think it was question 4, to, um, describe whether you thought there was a significant difference between the high amplitude and small amplitude waves. That phrase, significant difference, is very precisely used by scientists. They only use it after they've done a bunch of analysis with statistics. Because we got some variation in our times, right? And with statistics, we can look at how much variation there was. And that tells us if the differences between the two conditions, in this case, the large and small waves, it tells us if that difference was real or if it was most likely luck. Now, there's always a chance that it could have just been luck, so they would never say it was a real difference. They would just say it was a significant difference, and there was a less than 0.5% chance that it was just due to luck. So they would do this thorough analysis. And if we used more accurate measurement techniques, like if we had a detector that would actually time for us instead of relying on saying 3, 2, 1, go now, and using our fingers and the little delay that happens in our brain, if we had a more accurate way to measure this, physicists have found over and over again that the speed of the wave does not depend on how big the wave is. Small amplitude and large amplitude waves travel at the same speed, which is surprising to a lot of people, huh? I mean, I kind of think that when there's more energy in it, that it would go faster, but it's actually the same speed. Now, we could actually, it turns out, change the speed of that wave. If I took this Slinky and I stretched it out even tighter, what do you think that would do to the wave speed compared to if it was a loose Slinky? That would change the speed of the wave. It's more about the medium that it's moving through and less about the wave itself. For example, the speed of sound, like I said, is about 750 miles an hour in the air, but in water, it's like twice as fast. And then in a solid, it's even faster. If you put your ear down on this table over here and we plugged your other ear and I knocked on it, you could hear it right through the table, couldn't you? And it actually goes faster than sound moves through air. So the speed of the wave is less about the wave itself than it is the material that it's moving through, the medium. In fact, when I say speed of sound is 750, that varies with temperature. And I think it may also vary with the amount of moisture, the humidity in the air. Okay, so read and highlight those two paragraphs, and then go ahead and answer question 6. When you're done with 6, let me know. You guys online, please give me a thumbs up when you're done with question 6. And then we have to go back to the video for number 7. Okay, for number 7, we're looking at how many times the wave bounces. So I start the wave, it hits the wood and bounces back to my hand. Then it bounces off my hand and heads towards the wood again, huh? We could actually measure that distance. And which do you think would continue further? Which would bounce more times, the large amplitude wave or the small amplitude wave? Or would they both be the same? They're traveling at the same speed, but now we're looking at their distance, how far they went. How many times did they bounce? So let's look at that. Go. Now. And again, 3, 2, 1, go. Now. When I say now is when it gets back to my hand. That's when you stop your stopwatch. Last one. 3, 2, 1, go. Now. Now, one thing you might have noticed is how much the reflection continues. How many times does it bounce when I do the small amplitude wave versus the large amplitude wave? Here's the small. Watch how much it bounces. Here's the large. How many times did that bounce back and forth? Did you see the difference? Wave, large wave. So which one had more energy in it? Which one had more power? In way, okay, go ahead and answer question 7. I'm thinking about it like power because here's the small. Watch how much it bounces. Here's the large. How many times did that bounce back and forth? Small wave, large wave. So which one had more energy in it? Which one had more power? In a way, I like thinking about it like power because this idea of amplitude is what we compare to volume when it comes to sound. The higher the wave, the bigger the difference. Replay it? Yeah. Wave versus the large amplitude wave. Here's the small. Watch how much it bounces. Here's the large. How many times did that bounce back and forth? Small wave, large wave. So which one had more energy in it? Which one had more power? Okay, and then we're going to move on to number 8, comparing amplitude to volume. And I want to remind you that sound waves are a little different than light waves. For sound waves, we would draw them showing air molecules being compressed and then stretched apart and then being squeezed together, being stretched apart. So here they've squeezed together 3 times, right? We call these the zone of compression. And in between where they're stretched apart, it's the zone of rarefaction. So do you guys, when on the exam, you were asked to draw a loud wave and a quiet wave, and hopefully you did something like that, huh? The taller amplitude is the louder wave. And the smaller amplitude is the quiet wave, correct? Well, you can think about the same thing for light, except now for light, it's more like the wave that we're used to thinking about, right? More like the wave of the water would look like. And we're going to talk more about this in a minute. But you can see the height of the wave is the amplitude. And this would be like the brightness of the light. But for question 8, it's asking about sound. So here we go on that. In a way, I like thinking about it like power because this idea of amplitude is what we compare to volume when it comes to sound. The higher the wave, the bigger the difference between the top and the bottom, the louder the sound will be. It has more power. All right, now how did you do with your hypothesis? What happened in our results? What conclusions can you draw about the speed of the wave when it's small versus large amplitude? Okay, go ahead and do, well, it's got 2 number 8s there, doesn't it? Do both number 8s. So do the number 8 comparing volume to amplitude, and do the second number 8. Where you draw a large amplitude and a small amplitude wave. I think it would be a good idea if you included a label showing amplitude. For example, if I did this label, that would not be amplitude, would it? That's wavelength. So we don't want to see that, but to make it clear, you want to show this is the amplitude. So include those labels on there. Let's see. So I'm talking about showing a wave and labeling the amplitude, showing how tall it is here. Yeah. Okay, so we're going to move on and get started on the next section. We won't finish it today, but we'll get started on it. And I just want to remind you, whether you're at home or whether you're here in the classroom, when we're doing something like this and it's on a video, if you fell behind or you missed something, go watch the video to make it up, right? I'm also recording this class today, so the whole thing will be there, and you could just zoom to the section you needed to make up, right? At any rate, I'll post the link to this recording later. But what we're going to do now is talk about two different kinds of waves if we go on to the next page. So here's some vocabulary for you: transverse and longitudinal waves. And these terms, transverse and longitudinal, are not limited to waves. There are a couple good words to know. Like I used to teach anatomy, and we use these same things talking about the body. So for example, something that's transverse goes across something. So from shoulder to shoulder, that would be transverse. It's going across my body. Longitudinal is going the length of something. So from head to toe, that would be longitudinal in anatomy. And the same thing is going to be true for the waves. Does the disturbance that created the wave go across the wave? Transverse. Or does it go in the same direction as the wave? The length of the wave? Longitudinal. So you could also think of these as parallel or perpendicular. Perpendicular would be transverse. Parallel would be longitudinal. So let's go back to the video and pick it up where we left off. At the end of the previous segment, I mentioned sound waves, and I don't want to mislead you about them because I was not demonstrating a sound wave. There are two different kinds of waves. We call them longitudinal waves and transverse waves. Longitudinal means it goes the length of something, and that's what a sound wave does. Transverse waves go across something. And that's what the other type of wave I was demonstrating showed. That's the type of wave you see on the surface of the lake, or that you have with light moving through space. So let's look at. Okay, so you should be able to do what? Questions 1, 2, and 3. I'll back it up again. Play that again so you can make sure you get those answers 1, 2, and 3, because during that I will tell you about sound and light and water at the appropriate time. Okay, so listen for what kind of wave it is to answer number 3. I mentioned sound waves, and I don't want to mislead you about them because I was not demonstrating a sound wave. There are two different kinds of waves. We call them longitudinal waves and transverse waves. Longitudinal means it goes the length of something, and that's what a sound wave does. I just told you the answer to what? 3, who's that, A, B, or C that was sound? A. Did you get that? You need it again, or are we good? I mentioned sound waves, and I don't want to mislead you about them because I was not demonstrating a sound wave. There are two different kinds of waves. We call them longitudinal waves and transverse waves. Longitudinal means it goes the length of something, and that's what a sound wave does. There it was. Which one was it? Sound is what? Longitudinal or transverse? Longitudinal. Yeah, sound is a longitudinal wave. The disturbance is parallel to the motion of the wave. So it's like this. As the air molecules are vibrating back and forth, the wave is moving in the same direction, huh? The disturbance is the vibration, correct? And the vibration is going this way. But the wave is also going that way, huh? That's what I mean by being parallel. It's a longitudinal wave. On the other hand, transverse, the disturbance is up and down. The wave is still going the same way, but the disturbance is going up and down perpendicular to the movement of the wave itself. So which types of waves are transverse waves? Transverse waves go across something. And that's what the other type of wave I was demonstrating showed. That's the type of wave you see on the surface of the lake, or that you have with light moving through space. Okay, so I had two different examples of transverse waves. What were they? Water and light, both transverse waves. Okay, so the next thing we're going to look for is how the slinky is moved to make these two kinds of waves, right? So look at questions 4 and 5 so you know what to listen for. And let's go back to my garage. So let's look at this sound wave and how it actually does move. So first of all, the previous waves were like this. Notice I'm moving the slinky up and down. On the other hand, the sound wave is more like this. I move the slinky forward and backward. You can still see the wave bounce down there. It reflects off the end, just like an echo would bounce off of a cliff. But notice that the disturbance of the wave is moving in the same direction as the wave itself. The wave is going this way, and the disturbance is also going this way. That's why we call it a longitudinal wave. The disturbance moves along the length of the wave. On the other hand, okay, are we good with that one? So for what question was that? 4? How is the slinky moved to make a sound wave? How did I move it? Did I move it up and down, or did I move it back and forth? Might be phrases you could use. Did I move it forwards and backwards, or did I move it side to side? Right? And is that longitudinal or transverse? Yeah. And could you see that wave going okay? Could you see where the coils were squeezed together and where they were squeezed moved down the length of the wave? Where they were squeezed was the wave. And that location moved along the length of the slinky, huh? And then we're going to move on to the transverse wave motion. With light waves and waves on water, transverse waves, they move perpendicular to the length of the wave. So the wave itself is going in this direction. We can see that. It's moving from my hand to the wood and then bounces back. But the disturbance is going up and down. A transverse wave going across the direction of the wave itself. So we're going to do some experiments with transverse waves, but remember that sound waves are a different type of wave. Longitudinal waves going back and forth. And what we can see with the longitudinal waves is that we have a... All right, go ahead and do number 6. Wait, was that 6 or was it 5? It was 5, huh? Actually, you should be able to do number 6 now also. So one of those diagrams from number 6 is showing a transverse wave, and the other one is showing a longitudinal wave. So there's 2 arrows here. The big arrow shows the direction that the wave is moving. The small arrow shows the direction of the disturbance that created the wave. Notice one of the small arrows is perpendicular and one of them is parallel, huh? So you're supposed to label one of them as longitudinal and the other is transverse. Put that label above the wave. And then underneath the wave, add our 3 examples: light, sound, and water waves. Put those underneath the diagram. Put the examples underneath. You'll have 2 on one side and 1 on the other side, right? And then we're going to go back to the video to discuss the zone of compression and the zone of rarefaction. I know that word rarefaction is a big one, but notice the key part of it is rare. It means that something has become less common there, right? It's rare. Spot where the Slinky is all compressed. But remember that sound waves are a different type of wave. Longitudinal waves, going back and forth. And what we can see with the longitudinal waves is that we have a spot where the Slinky is all compressed. We call that the zone of compression. The same thing happens with air molecules, with a sound. And then we have another spot where it's all stretched out, the zone of rarefaction. The molecules become more rare, I guess you could say. So this is what happens with sound waves. Is that good for describing zone of compression and rarefaction? I'll back it up to that section in case you want to hear it again. Otherwise, just go ahead and write your answer. Do some experiments with transverse waves, but remember that sound waves are a different type of wave. Longitudinal waves, going back and forth. And what we can see with the longitudinal waves is that we have a spot where the Slinky is all compressed. We call that the zone of compression. The same thing happens with air molecules, with a sound. And then we have another spot where it's all stretched out, the zone of rarefaction. The molecules become more rare, I guess you could say. So this is what happens with sound waves. They get compressed and they get spread out in the zone of compression and the zone of rarefaction. And we can see that zone of compression moving down the length of the Slinky and then echoing back to me. Okay, here it is zoomed in of that longitudinal wave. So can you see the zones of compression there where the coils are squeezed together? And then between the zones of compression would be the zones of rarefaction. So what I would like you to do is number 7 and then number 8. And that will be a good stopping place for today. Remember that basically if it's a longitudinal wave, we're doing a sound wave, right? We're not doing our typical transverse wave like water. So it looks a little different, but you can think of it in a similar way. I would just use parentheses to draw this wave. You could use a pencil and draw them too, but like if you go in there and use a parentheses and maybe you make it bigger, just make the font bigger. But basically we have a zone of compression, and then ideally we show some spread out. That's our zone of rarefaction. And then you have another zone of compression. I usually show 3, but it might be better to show more. And then they're spread out again. And then we have another zone of compression. This distance should be about the same as this distance. That wavelength should be the same. So that's what a longitudinal wave should look like. And you should label zones of compression, zones of rarefaction. This should be review from what we did at the end of the last semester, right? Last month. Something like that. Then you should draw an arrow to show the direction that it's moving. You can also label other parts, the amplitude, the wavelength, things like that. But mostly I just want you to label the zone of compression where they're squeezed together and the zone of rarefaction where they're spread out. And you could think of this like water waves if you think of each zone of compression as being the peak of the wave. So we have a wave comes up here, peaks, and then it drops down, comes up here and peaks, drops down, comes up here and peaks again. That might be another way to cement in your mind how this is similar to waves on water or light waves. If you think of the zone of compression as the peak. When you're done with that, there's a few minutes left in class, and I would invite you to go back to that page 2 and finish up your abstract art diagrams. Let me know if there's anything that you need me to repeat. And you guys at home, that's all we've got for today. Thanks for sticking with us. Let me know if you have any questions, and I imagine I'll see you in a couple days, huh?